Welcome. So last time we saw chapter number 9, and that was 1 and 2 sample estimation, estimating the variables. And today we are going to start with chapter number 10, almost the same thing, 1 sampling, 2 sampling, but not for the estimating the variables. But we are going to see here the test of hypothesis. So not the variables, but now not the estimation, but now the test of hypothesis. So that's what we are going to see over here in this chapter. So let me start with this one. Article 10.1, 2, and 3, they are just the introductory portion, because mainly we are going to see Article 10.4 and 5, that is 1 sample test of hypothesis and 2 sample test of hypothesis. So that's what we are going to see now. So, but before that, just very briefly, I would like to go over article number 10.1, 2, and 3. And then after, we will go over the detail of article 10.4 and 5. These are the rest of the things in last chapter, which we don't want to go for this one. And we did the examples also and everything that was done in the last chapter. And this is your new chapter, that is your chapter number 10. So 1 and 2 sample test of hypothesis. So first of all, let me let you know that what is the difference about the scientific system and what we mean by actually this test of hypothesis. So for example, a medical researchers may decide on the basis of experiment evidence whether coffee drinking increase the risk of cancer in humans or not. An engineer might have to decide on the basis of sample data whether there is a difference between the accuracy of 2 kinds of gauges, or a sociologist might wish to collect appropriate data to enable him or her to decide whether the person's blood type and eye color are independent variables. In each of these cases, you can see here, the scientist or engineer postulates or conjectures something about the system, and each must make use of experimental data and make a decision based on the data. And in each case, the conjecture can be used or can be put in the form of the statistical hypothesis. So that's what we mean by the hypothesis, statistical hypothesis. And we are going to learn over here mainly 2 types of hypothesis. One is null hypothesis. We denote that is by capital H suffix 0, and the alternating hypothesis, that is capital H suffix 1. Null hypothesis, that is always with relates with your mean value, means null hypothesis, that is always the equality. And alternating means which is not null, which is not related to mean, but different than this one. So that is called alternating hypothesis. So mainly we are going to see over here that if you accept null hypothesis, that means automatically you are going to reject, or you are almost leading to reject the alternating hypothesis, and the vice versa. If you are accepting the alternating hypothesis, means you are leading to reject to the null hypothesis. We are not some statistical language used over here in this book that is a little different. Fail to reject null hypothesis means a kind of acceptance. So please keep this thing in mind. Fail to reject null hypothesis means we mean by the acceptance of the acceptance of null hypothesis. Okay, so procedures and that leads to acceptance or rejection of statistical hypothesis, such as this, comprise a major area of the statistical inference. And let's first start with, because as I told you, the statistical hypothesis. So let's first start with the statistical hypothesis definition. Statistical hypothesis is an assertion or conjecture concerning one or more populations. So again, statistical hypothesis is an assertion or conjecture concerning one or more population. And then after, we are going to see very briefly about the hypothesis, or what we mean by the rejection of the hypothesis. So rejection, you can see here, the rejection of a hypothesis implies that the sample evidence refutes it. Another way we can put like this, the rejection means that there is a small probability of obtaining the sample information observed when, in fact, the hypothesis is true. So when our probability is extremely small, 0.002, so that means we have enough evidence to reject that hypothesis, right? If probability is 0.8, so very, probably maximum probability is 1, minimum is 0. So if it is very nearer to 0, 0.0001, 0.002, something like that, it's very, so almost we can say that event is not going to happen. That means the hypothesis, you can, whatever we have considered, we can reject that hypothesis. But if the probability is suppose 0.7, 0.6, 0.7, 0.8, 0.8 is really good, strong probability. And that's why we can accept that hypothesis. So that's what we are going to see in this chapter. On the other hand, it is very important to emphasize that the acceptance or rather failure to reject does not rule out other possibilities, just to let you know this thing. And then after we are going to see the null and the alternating hypothesis. I told you null hypothesis, that is H0, alternating is H1. But here it is given the structure of hypothesis testing will be formulated with the use of the term null hypothesis, which refers to any hypothesis we wish to test and is denoted by H0. The rejection of H0 leads to the acceptance. It's not exactly, but rejection of H0 leads to the acceptance of the alternating hypothesis H1. Right, guys? And the alternating hypothesis H1 usually represents the question to be answered or the theory to be tested. And thus its specification is crucial. The null hypothesis H0 nullifies or opposes H1 and is often the logical complement of H1. I repeat, the alternating hypothesis H1 usually represents the questions to be answered or the theory to be tested, and thus its specification is crucial. The null hypothesis H0 nullifies or opposes H1 and is often the logical complement to H1. Right, guys? So actually we can do this thing in this way: the reject H0 in favor of H1, reject H0 in favor of H1 because of sufficient evidence. Reject H0 means in favor of H1 means you are going to accept H1, right? So reject H0 in favor of H1 because of sufficient evidence in the data. Or fail to reject H0 means you are accepting now H0 because the insufficient evidence in data. Now you have this H0 may be two-sided, maybe one-sided. If it is strictly greater than 0, it is on right side. If it's strictly less than 0, it's on the left side, right? So here you can see in this example, H0 is your mean value P. So P is equal to 0.10 and H1 equal to P greater than 0.10. If you read this one, I'm sorry, guys. Excuse me. Let me have something. Just give me a break of a minute. Sorry, guys. So let me continue. As I told you that if you read this example, note that the conclusion do not involve a formal or literal accept H0. The statement of H0 often represents the status quo in opposition to the new idea, conjecture, and so on. And stated in H1, while failure to reject H0 represents the proper conclusion, right? Good. That's fine. So as I told you that it should be just one-sided or two-sided like this, right side if it is strictly greater than the mean value or H0 value. Anyway, guys, then testing a statistical hypothesis. So testing statistical hypothesis, as I told you that here we are going to rely on a kind of probability. You can see over here the test statistics. If your probability is 0.25, right? And if P equal to 0.25, P equal to 0.25 and each one equal to P greater than 0.25, right? So that is one of the examples given over here. I think you can read this one, not a big deal, very simple thing. And here I just would like to go over the probability of an error of type 1. We are going to see two types of error. One is type 1, second one is type 2. Type 1 error I would like to define by alpha. Type 2 error I would like to define by beta. So rejection of the null hypothesis when it is true is called type 1 error. You won't understand this thing unless I explain to you. Rejection of null hypothesis, right? If you reject null hypothesis when it is true, right? That is called type 1 error. Fine. Second definition is the non-rejection of the null hypothesis when it is false. That is of type 2 error. But I would like to summarize this definition 10.2 and 10.3 in this format. Look at over here. If you consider this table, it would be now very much clear to all of you, to you guys, that what we mean by type 1 and type 2 error. Suppose H0 is true. Whatever H0 you have fixed, you have decided H0 is true. H0 is true and you don't reject it. Because H0 is true, do not reject H0. That's the correct decision, right? But even though H0 is true and H0 is true, and even though if you reject H0, that is the type 1 error. So that's what it means over here, the rejection of the null hypothesis. When it is true, but even though you are rejecting null hypothesis, that is called type 1 error. Same over here, that suppose you have H0 is actually false. Try to read like this. H0 is actually false. And if you do not reject H0, it is false and you are not rejecting as it is false means you need to reject that one. But if you don't reject H0, even though it is false, that is called type 2 error. And if you go back and try to read definition 10.3, non-rejection of the null hypothesis when it is false, see, that is type 2 errors. Type 1 error, I mean to say, as I told you, that there is nothing but we denote by alpha, and second one, this is your beta. And H0 is false, and if you reject it, that's the right decision, correct decision. Right, guys? And we always try to find the probability. If you are looking for probability, that means you rely on kind of binomial distribution, or you can say normal distribution. If it is graph is normally distributed, in that case, of course, you can go for normal distribution. Once you talk about the normal distribution, that means again, you have two choices, that your variance is given, right? If variance is given, that means you can convert your data in terms of the Z distribution and use table A3. If the variance is not given, and in that case, you are going to take help of statistical variance. And in that case, we rely on chi distribution, means T distribution, and we are using table A4, I think so. Yeah. And then after, we are going to repeat the same process for multiple samples, double samples, 2 samples, right? And that will be the end of the syllabus, at least for this elementary course of statistics, probability and statistics. Right, guys? Okay, so let's start with, so I hope you understood this type 1 and type 2 error. So probability of type 2 error, the type 1, type 2, everything is mentioned over here. Now, guys, look at over here that once you have this one, then after what I'm going to do, let me just go for role of alpha, beta in the sample size. Whenever you are facing type 1 error, again, whenever type 1 error, that means H0 is true, but you are rejecting H0. Even though it is true, you are rejecting H0. That is type 1 error. When that means type 1 error, that means even though H0 is true and you are getting probability is extremely small, right? If you count the probability, you are going to get extremely small value, 0.001, 0.002, something like that. That means you need to reject H0 based on this probability, but that is not the actual case. So what we are going to do, how can you overcome this situation? We are going to increase the sample size. Suppose in the problem, the sample size, as for example, sample size is given to you 10. I'm going to increase to 100 or 200 or 300 like this. If you increase sample size randomly like this, in that case, or drastically just increasing the sample size, in that case, you can come over this type of error. Error of type 1 means H0 is true ultimately, and then after making big N sample size, if you again count the probability, if you are getting it, quite possible that you are getting the probability. Previously, it was 0.002. Suppose now it is 0.7, 0.5, 0.6. More than 0.5 is good, right? So whenever we have this type of situation, in that case, we always say that increasing the sample size means we are removing the or decreasing the error of type 1, right? Means H0 is true and we are accepting, we are leading towards the acceptance of H0. That is your error alpha. Now I explain to you about the error beta. Error beta is nothing but your mean value. Suppose in some of the examples, now let me just go through this one because unless I show you the picture, it won't be very much clear to you. Look at over here, guys. In this particular problem, one problem is given to us. I am not interested in the problem because right now I'm interested only in this type of data. Okay, my mean value is this one, right? And I'm converting that one in terms of my z-score. This is my x bar. This is my nu equal to 25 in this particular problem, and divided by sigma over square root of n or whatever it may be. And I'm getting my z-score 2.66. So if I find the z equal to 2.66, so my alpha will be z equal to 2.5, means H0 is 2.66. H0 is 2.66. Based on this problem, if you read this problem, you will come to know, it says that the probability of committing both types of error can be reduced by increasing the sample size, as I told you, right? Consider the same problem using, that means just the previous problem is continuing over here. So that's what we are doing over here. Look and see, guys, that we have a normal distribution with new value 25 and sigma equal to 4.33, right, guys? And after converting to z score, I am getting z equal to this one. So my error alpha equal to, I don't want to write alpha, just find p x greater than 36 when probability is 1/4, or that is z is greater than 2.66. If you use table A3, z equal to 2.66, you are going to get that is equal to point. This is greater than means you can write 1 minus probability of z less than 2.66, just like your previous chapters. So it is 1 minus 0.9961, and you are going to get 0.0039. See, probability is extremely low. Because this probability is extremely low, no one is going to accept this event. So that's why I would like to say that is event alpha, that is error alpha. But now what I'm going to do, previously my sample size, what was the sample size? Is it mentioned somewhere over here? My n value, p and 36, all possible scores about 36 constitute critical region. Okay, fine. So let's find this one. And now I'm going to start with this one. Look at here, guys. So if H0 is false and the true value H1 is equal to half, determine the probability of type 2 error. That is okay. So here he mentions type 2 errors, and I think it is better if I take the example after some times, alpha and alpha 2. He in the book, actually, he has explained, the authors have explained only type 1 and type 2 errors, and then the example, if I'm not wrong. So type 1 error is just can be removed just by increasing the sample size. Now type 2 error. Type 2 error here you can see by mean value nu equal to 25, and this mean value nu equal to 25, I can increase that mean value to 50. Right? That is type 2 error. Type 2 error, again, let me remind you that suppose H0 is false, and even though you do not reject H0, your null hypothesis, that is called type 2 error, right? So type 2 error can be removed, can be minimized just by increasing the mean value. So here mean value in this problem was 25. I'm increasing this mean value to 36.5 or 50 like this, right? And then after again, I will go for z-score and like this until I get the good probability, means more than 0.5. So that is how we can, this is type B error. Look at here, type 2 error, that is beta, and that is given like this, right? For 25, probability is extremely small, 0.0035. But again, you can get out of this situation, come over this situation just by increasing the mean value, right, guys? So here the illustration with a continuous random variable. Now I think we are much more interested in this example to understand type 1 and type 2 error. Usually people don't bother about this thing, but it is equally important. It says that, let me start from here, consider the null hypothesis that the average weight of male students is in a certain college is 68 kilograms. Now see, average weight of a male students means is mu value, right? New value is given to us. And as I told you, new value is nothing but your H0. So I would say that H0 equal to nu equal to 68. And kilograms against the alternative hypothesis. Now 68, when somebody says that it could not be 68, it could be less than 68 or greater than 68, right? So here it works on both the sides of your normal distribution. So let me write H1 equal to nu different from 68. Whenever you're strictly greater than, at that time we just go for alpha, Z alpha. If it is both the sides, in that case, we go for Z alpha by 2. You know this thing better because we went over this type of stuff in chapter 8. Okay, good. So H0 equal to nu equal to 68 and H1 equal to nu not equal to 68. So see, do not reject H0. When nu equal to 68 means H0 is this one, nu equal to 68. So the range here we have, that is 67 to 69. Do not reject H0. But if it is not equal to 68, it goes like this and like this. In that case, you can reject H0, right? Reject H0. That's fine. That is not the concern. Concern is over here. I would like to read this thing. Assume the standard deviation of the population of the weight to be sigma equal to 3.6, right? So we are going to use sigma equal to 3.6 for the large samples. Now, large sample is already given to us. We may distribute S for sigma if no other estimation of sigma is available. Our decision statistics based on a random sample of size n equal to 36. So my n equal to 36 will be x bar, the most efficient estimator of nu. From the central limit theorem, we know that the sampling distribution that is equal to sigma divided by square root of n, that is equal to sigma x bar, and that is equal to 3.6 divided by 6, that is equal to 0.6. So that is my denominator, you know this thing, right? So my alpha is x bar is either less than 67 or it is greater than 69, because I just for the sake of convenience, I took my nu equal to 68 within the range of 67 to 69. So it is less than 67 and greater than 69. Or you can say different from 68 means you can say less than 68 and greater than 69, less than 68 and greater than 68. But in a practical purpose, you have to have a little window with the integers. So I would say that it is 67 to 69. So less than 67 reject null hypothesis, greater than 69 reject null hypothesis, but within the range of 67 to 69 accept null hypothesis, or you can say don't reject null hypothesis. Okay, so here it is like this, and here it is my mean value, and here it is 67 and 69. They are, you can see over here on the left of this one 67 and right of 69. So my probability x bar less than 67 when nu equal to 68 and greater than 69 for nu equal to 68. That means I'm finding z score for this one as well as z score for this one. So I have to go for z1 and z2. If I want to go for z1, that is equal to x bar. X bar is now 67. X bar minus nu value is 68 divided by sigma over square root of n, central limit theorem, that is 0.6, just we saw on the previous page, right? 0.6. So let me adopt that value over here. And z2 equal to now 69 minus 68 divided by 0.6, and that is 1.68. So I can find that z is less than this is negative 1.69, and z is greater than negative 1.67. That means ultimately the same region is there on the left and the right. That means I can multiply it by 2. So z, 2 times probability of z less than 1.69. Always try to go for less than, because probability starts from the most left part of the normal distribution curve. So that's why if you use your table, you are going to get 0.0950. 0.09, guys, not even 0.1. It's extremely low. That means just 9.5%. It says that 9.5% of the samples of size 36 would lead us to reject nu equal to 68. right? 9.5% of all samples of size 36 would lead us to reject nu equal to 68 kilograms, where in fact it is true, right? To reduced alpha means alpha is this one. Alpha is the probability. Probability is small, very, very low, right? To reduce alpha, we have a choice of increasing the sample size or widening the fail to reject region. Means widening your mean value. Sorry, guys. Suffering from cold, allergic cold. Yes. Anyway, so Z is this one. So what we are going to do, you can see over here that 95% of the sample size 36 would lead us to reject nu equal to 68 kilograms, when in fact it is true. To reduce alpha, we have a choice of increasing the sample size, right? Increasing the sample size, widening, increasing the sample size, I mean to say, or other way around, widening the fail to reject region. Suppose that we increase the sample size n equal to 64. Now it was 36 now. Previously it was 36. Now I am increasing n equal to 64. If you write n equal to 64, that means this denominator will be changed because it is sigma over square root of n by central limit theorem. And here also these changes are there. This numerator remains the same in both the cases. Denominator will be different. So here Z1 equal to negative 2.22 and Z2 equal to 2.22, right? Both the sides you have same region. So that's why again you can use the same logic. Alpha equal to probability of Z less than negative 2.22 plus greater than 2.2. So it is 2 times less than. Use table A3 and you're going to get 0.0264, right? Now after increasing my sample size, almost I made it double, even though it doesn't give us the proper probability, proper estimation, 0.0264. So I would say that the reduction in alpha is not sufficient by itself to guarantee a good testing procedure, right? And we must also calculate now beta, my second error. So how I'm going to get my beta? Just look at over here, guys. We must also evaluate beta for various alternative hypotheses if it is important to reject H0 when the true mean is some value nu greater than or equal to 70 or nu less than or equal to 66. Now look at over here. My mean value here 68. Now it is now 69. So let me just increase it greater than 70. Greater than or equal to 70 or less than or equal to, let me take, don't increase this is rapidly, just increase just by 1 or 2 digits. So 66, so let me go over here for 66. So less than nu, less than or equal to 66. Then the probability of committing a type 2 error should be computed and estimated for the alternative nu equal to 66 and nu equal to 70. So now my x bar minus nu, my new value is now different, right? X bar minus nu divided by sigma over square root of n. Okay, guys, so let's count this one. So my now type 2 error beta is equal to 67 is less than x is less than 69, nu equal to 70. Okay, so now my new value, previously it was, look at over here, it was 68. Now I have changed this 68 to 70, right? Within the range of 67 to, so this is 67, this is 69, but my mean value, I would like to take it over here. So my mean value is now 70. Look at over here. My mean value is where I was. Yes, that is 70. So this remains 67, this remains 69, just like the previous case, but mean value have changed. I have shifted from 68 to 70, 68 to 70, I have shifted, right? And I calculated my beta. If you calculate your beta like this, using your mean value, increasing mean value little bit, 68 to 70. So beta equal to this one. Again, use table A3 and you're going to get 0.0132. Right, guys? So if the true value of nu is alternative nu equal to 66 and the value of beta will again be 0.01, again 0.0131 is really less. Doesn't solve the purpose. For all possible values nu less than 66 and nu greater than 70, the value of beta will be even smaller when n equal to 64. Right? If you take n equal to 64, this value will be more smaller, and consequently there will be a little chance of not rejecting A0 when it is false. Right? But now let me do one thing. 70 doesn't work. 70 doesn't work. 68 doesn't work. 70 doesn't work. But it could be possible that if I go for little large value, 68.5. And let me try for this one now. So my all other values are same. G1 67, X bar 69. Here instead of 70, I would like to go for 68.5. 68.5. So if you go for 68.5 with the same sample size, right, 0.45, just like your previous case, 0.45, sample size n equal to 64, right? Already you took sample size larger, n equal to 64, than the given. Given was only 32 and now it is 64. Okay, and we are now shifting this one. We shifted 68 to 70, didn't work. Let me just make a small change, 68.5, my new value. So if you increase this new value 68.5, you are going to get Z1 and Z2. Find Z score again for Z1 and Z2 and beta error. Calculate this one using table A3. See here, drastic changes. You are going to get 0.8661, 0.8 out of 1 probability, guys. Very strong probability. You have to accept this one. So this way you can remove the type 1, type 2 error and try to come to the proper conclusions. Look at over here. So 68.5 mean, and this is the 69, this 68 and 69, whatever it may be, that is this one, right? So your confidence interval you can find like this. So preceding example illustrates the following important hypotheses. These hypotheses are like this. The type 1 error and type 2 error are related with each other, right? Because by using increasing number sample size 64, I change my mean value little bit larger and smaller both ways, and I got the correct answer. So they are related to each other. A decrease in the probability of one generally results in an increase in the probability of the other. The size of the critical, right? Because you know this thing, decrease in the probability of one generally results in increasing the probability of the others, right? The size of the critical region, and therefore the probability of committing type 1 error, can always be reduced by adjusting the critical value. Right, by critical values. Okay. The increase in the sample size n will reduce alpha and beta simultaneously. Increase means increasing the sample size n will reduce alpha and beta, means error. It reduces the error. Don't say probability. It reduces the error. If the null hypothesis is false, beta is maximum when the true value of the parameter approaches the hypothesized value. The greater the distance between the true value and the hypothesized value, the smaller beta will be. Okay, so type 1 error alpha increase the sample size and type 2 error beta increase or decrease the mean value, right? Nu or sample mean X bar. Okay, the power of the test is the probability of rejecting H0 given that the specific alternative is true. Specific alternative is true. And let's go for this example, 1 and 2-tailed test. 1-tailed test means H1 theta is strictly just on one side, strictly greater than 0, theta 0, strictly less than theta 0. That is called 1-tailed because we have just left or right or left side. And if not equal to 0, in here we are going to find just Z alpha. Here we have to find the alpha by 2 because they are same on both sides. Theta is not equal to theta 0. So please keep this thing in mind. And I would like to switch over to some examples. So example 10.1, just the example based on 1 and 2-tailed test. It's not a big deal. So example says that a manufacturer of a certain brand of rice cereal claims that the average saturated fat content does not exceed 1.5 grams per serving. State the null and the alternative hypothesis used in testing this claim and determine where the critical region is located. Okay, so 1.5 grams does exceed 1.5 grams, means if it exceed 1.5 gram, you have to remove that one. So your does not exceed 1.5, that means it has to be less than 1.5. So for that you are good. If it exceeds 1.5, you are not. So that's why I have to arrange my H0 nu is greater than 1.5. Look at here, guys, please. Don't say nu less than 1.5, because nu less than 1.5, that means it would be coincided with your H0. So please keep this thing in mind. So manufacturer of a certain brand of rice cereal claims that the average saturated fat content does not exceed 1.5 grams from serving. State the null and alternating hypothesis to be used in testing this claim and determine whether the critical region is located. The manufacturer's claim should be rejected only if nu is greater than 1.5, right? So it is rejected. What is my nu? H0? H0 is equal to 1.5. Greater than 1.5, claim is rejected, right? So if nu is greater than 1.5 milligrams and should not be rejected if nu is less than or equal to 1.5 milligrams. So we can write like this: non-rejection of H0 does not rule out values less than 1.5. See, non-rejection of H0. You are not rejecting H0. Suppose non-rejection of 0 does not rule out values less than 1.5 milliliters. Right? Since we have one tail test here, the greater than symbol indicates that the critical region lies entirely to the right tail of the distribution of our test statistics X bar. Test statistics X bar. Let's go for the second example. Second example says that a real estate agent claims that 60% of all private residences being built today are 3-bedroom houses. The test size claim a large sample of new residences is inspected. The proportion of those homes with 3 bedrooms is recorded and used as the test statistics. State the null and the alternative hypothesis to be used in this test and determine the location of the critical region. If the test statistics were substantially higher or lower than p equal to 0.06, right? Now p equal to 0.06, that is your mean value. So that is your H0, and outside it is your alternating hypothesis. So here alternating hypothesis implies a two-tailed test with the critical region divided equally in both tails of the distribution of P, our statistics. Another part is the use of p-values for decision-making in testing hypothesis. Means probability value. Only I mentioned to you that the probability 0.0 is extremely small. That means in that case, you can reject null hypothesis, right? And you can accept the alternative hypothesis. So p-value approaches has been adopted extensively by users of applied statistics. And that sounds good. And now I just would like to go for some rules, and then after, if possible, we can go over one of the examples over here. Actually, it is not required, but if you want, we can go over one of the examples and we will stop, because I want to start article 4.5 and 10.4 and 10.5 together. That would be our last class for this course. So let me just go over this part, some rules. We are going to stop very soon. You can read all these things. That is just for the knowledge. The p-value is the lowest level of significance at which the observed value of the test statistic is significant, right? Observed value of the test statistic is significant. Approach to hypothesis testing with fixed probability of type 1 error. Okay, state the null and the alternating hypothesis H0 and H1. Choose a fixed significant level alpha value. Mostly alpha value will be provided to you. Choose an appropriate test statistics and establish the critical region based on alpha. Reject H0 if the computed test statistics is in the critical region, right? Reject H0 if the computed statistic critical region, that means probability is extremely low. Otherwise, do not reject it and draw significant scientific or engineering conclusion. The problems from where it is arised, you need to answer the problem in the same fashion, same way. And the significance testing p-value approach is the hypothesis testing and significance testing. State null and the alternating hypothesis. Choose an appropriate test testing. Compute the p-value based on the computed value of the test statistics. Use judgment based on p-value and knowledge of the scientific system. That's fine. These examples are not that difficult, but let's go over just one example I want to go over. That is example number, which one? Let's go for 10.9. If you guys agree with me, let's go for 10.9. Let's see. Okay, guys, so 10.9, and I just would like to just read this example, and then after we will be doing this thing. A dry cleaning establishment claims that a new spot remover will remove more than 70% of the spots to which it is applied. To check this claim, the spot remover will be used on 12 spots chosen at random. Your n value is given. If fewer than 11 of the spots are removed, fewer of 11 of the spots are removed, right? Please keep this thing in mind, guys. Okay, fewer of 11 of the spots are removed means I am going to consider my x value greater than or equal to 11, right? Greater than, or you can say h1 greater than or equal to 11. If fewer than 11 of spots are removed, we shall not reject the null hypothesis that p equal to 0.7. Okay, everything is given to you. Probability is also given to you. Otherwise, we conclude that p greater than 0.7. Okay, evaluate alpha assuming that p equal to 0.7. Evaluate beta for the alternative p equal to 0.9. Okay, guys, so let me just stop sharing this book and let me share my whiteboard so that we can solve this example. It says something like this. It says something like this, example number, which I said 10.9. So example 10.9, and it says that A part says that evaluate alpha assuming that p equal to evaluate alpha assuming that p is equal to 0.7, probability is 0.7. Okay, here in this example, you know that n equal to 12 is given to us, probability is 0.7 given to us, and my alpha is equal to probability x greater than or equal to 11, and probability of x greater than or equal to 11, that is nothing but, yes guys, that is equal to, how can you find? Just use your table and you are going to get that is equal to 0.0712 plus 0.0138, and if you add this, we're going to get 0.3529. And same way I can find my beta, my b, so that is n equal to 12 and p equal to now 0.9. So my beta is nothing but probability of x less than or equal to, it says now, probability of x less than or equal to 10, because it's 11 here, so here it is 10, and that is equal to, if you find probability less than or equal to 10, here you can write, okay, that is equal to 0.34110. So that's really simple. I don't think that it is required. And if we want to go over, suppose, example number 10.10, repeat x. This, okay, there's 10.10 that is also in the continuation of 10.9. So let me go for this example also because that is in the continuation. It says that assume that, repeat exercise 10.9, but assume that 100 spots are tested and critical region is defined, dx is greater than 82, where x is the number of spots removed, right? X is strictly greater than 82, where x is the number of spots removed, and you are given now n equal to 12, n equal to 100. So my example 10.10 says that A part, n is equal to 100. My p was 0.7. E was 0.7. What is my nu? Nu is equal to np, right? Chapter 4. That is equal to n and p. So if you multiply this one, I'm going to get 70. And my sigma was square root of npq, if I'm not wrong, npq. And that is equal to square root of n equal to 100. P probability is equal to 0.7. And you know that P plus Q is equal to 1. So naturally Q is equal to 1 minus P. So 1 minus 0.7. So that is equal to 0.3. So Q equal to 0.3. Q equal to 0.3. And that is equal to 2.73. 2.73. Right? So I can find my Z value. Z is equal to now. Okay. I can't see here. Z equal to what are the values provided to us? It says something, okay, x is greater than 82. You are given x is greater than 82. So I would like to consider x bar equal to 82.5, suppose. So it is 80 x bar 82.5 minus nu equal to 70, as I told you, divided by sigma square root of n, that is equal to 2.73 divided by square root of n is 10. So 2.73 divided by 10, right? Is it 10? No. Sigma over square root of n. So that is equal to x bar minus nu divided by sigma. And sigma is equal to sigma over square root of n. So you are going to get that is equal to 0.273, right? So if I'm not wrong, let me just write it down. So 0.273 and 0.273, approximately you're going to get 0.3410. So my alpha is equal to probability of x greater than 82 is equal to probability of z score is greater than 2.73, right? Z score is greater than 2.73 and z score is greater than 2.73. Is it 2.7? Z score is 3410, right? I'm sorry. So Z score is greater than 3.10. Probability of Z score is greater than 3410, and you can find that is equal to 1 minus probability of Z is less than 0.3410. You're going to get 1.0.9968, and that is equal to 0.0032. So that is your, I think, A part. This is your A part. Same way I can go for the B part. B part is nothing but now n is equal to 100, and but P is equal to now 0.9, and my nu is equal to NP. N is equal to 100, 0.9, so it is naturally 90. So my sigma equal to square root of NPQ. So that is equal to now square root of 100 times P equal to 0.9. So naturally it is 0.1 over here. And that is equal to 3. 0.1. So that is equal to 3. And therefore my Z score is nothing but x bar minus nu divided by sigma over square root of n. Right? So that is equal to x bar minus nu divided by sigma over square root of n. Sigma over square root of this is samples are given to us, right? Okay. So here you're going to get that is equal to 82.5 minus 90 divided by sigma over square root of n, that is equal to 3 over 10, so 0.3, and approximately there is negative 2.5. So my beta value is nothing but probability of X less than or equal to 82, and that is equal to probability of Z is less than negative 2.5, and that is equal to 0.0062. Probability is extremely low, right? So that's how you can solve the examples. Nobody's going to ask you this type of things anyway, but that is simple. So let me just save this one and in a folder, and I think we can conclude today's class because I don't want to start the new article now. Last article 10.4 and 5 will be done next time. Thank you so much, guys. Thanks for your patience. And now let me just save this one. Let me close this one. And let me stop recording. Thank you. See you next time, guys.